This training session covers getting started with our monitoring and protection IC for high cell count batteries. The focus of this is the BQ76940 family of monitor devices and information helpful when designing with these devices. Additional information is available on TI.com. A lithium-ion battery system will have an AFE function to deal with analog voltages, an MCU to respond to the battery conditions, and FETs controlled by an appropriate driver with inputs from the AFE or MCU. The MCU can provide display or communication with the system. A fuse is present to limit current. Additionally, a battery may have a secondary protector function which can activate or open the fuse. Some TI gauges incorporate the AFE, driver, and MCU functions into a single package. This provides a simple, compact solution. The BQ40Z50 and BQ4050 support 3 to 4 cells. The BQ40Z80 supports 3 to 7 cells. The BQ76940 family device consists of the AFE to monitor cells and current and turn off FETs. A MCU is needed to enable the FET initially and on fault recovery. The MCU can also provide additional protections, gauging or measurement, and communications to the outside world. A high-side FET driver must be provided separately if desired. High-side switching makes communication simpler. The BQ76940 devices interface to the analog signals, so they have an analog front end or AFE. They also have ADCs and provide digital outputs, so they are called monitor devices. Both terms may be used in this presentation. There are 3 devices in the family for 5, 10, or 15 maximum cells. The BQ40Z50 or BQ40Z80 will typically be a smaller, more compact solution for a 3 to 7 cell system. The gauges have a fixed algorithm, however. If a customer wants to do something special with their battery outside the capability of the gauge, using a monitor with an MCU may be desired. Of course, a MCU could also be used with the gauge for other interfaces. The basic BQ76940 system, then, consists of the AFE to monitor cells and current and turn off low-side FETs. A MCU is needed to enable the FET initially and on-fault recovery. It can also provide the additional protections, gauging or measurement, and display. For a 2-terminal battery, low-side switching is simple. The MCU can also provide communications to the outside world. Communications need some special consideration discussed later. The block diagram is shown in the datasheet. At the top, there are 2 power inputs. The BAT pin provides power to a 3.3 volt regulator for most internal circuitry. The reg source pin supplies power for other circuits, including reg out, which is available for external use. On the left side are the cell inputs and temperature sense. These are measured with a 14-bit ADC. Current sense is shown on the bottom. There are comparators for current protections, as well as a 16-bit ADC for current measurement. Configuration data is stored in EEPROM at the factory. There is no EEPROM available for application use. The basic schematic for the BQ76920 consists of the power and cell monitor filters, a low-side sense resistor, low-side power FETs, and communication lines, which are I2C. When you look at the datasheet, you notice the part has multiple pins defined for power supply voltage. If you do solder X-ray inspection on your boards, you may notice extra wires inside the package. This is because the family uses one silicon die for each 5-cell group. The BQ76930 contains 2 die. The BQ76940, 3 die. The power for one group flows into the next group, and only an offset current is required at the middle pin. Supply and offset currents are shown in the datasheet. Reg source goes into only the lower group to power the FETs, interface, current measurement system, and supply the external regulator. This architecture will lead to some trade-offs for the system designer. What happens when you short-circuit a battery? There are really 2 types of events. In the first type, the battery current crosses the short-circuit threshold for the delay time, and the FETs are switched off. With a low short-circuit threshold, the cell voltages may not drop much, and things may stay basically normal. With a true short circuit, the battery voltage may drop quite low. 100 amps into a 100 milliohm test resistance would give 10 volts. Each cell input will pull current out of their filter capacitors and the lower group power filter capacitors. The power filter capacitors must be large enough to keep the device alive to time the protection event. After the input filter capacitors are depleted, current will be drawn out of the IC pins. The input current is limited by the filter resistors, which must be large with this architecture, so the internal cell balance current will be low. In this example, a 6-cell battery with the BQ76930 is shorted. The current quickly crosses the short circuit threshold and builds to approximately 130 amps. As the part is timing the short circuit delay, notice that the power supply voltages are dropping. The lower group voltage drops more quickly than the upper. After the short circuit delay, the discharge output turns off. There is some time required for the discharge pin to discharge the FET gate. The BQ76930 and BQ76940 devices have internal communications between the cell groups for control and voltage measurement reporting. This is good in that no board design is needed for the communication lines, but bad in that the designer can't see what it is doing. The device starts communication on a schedule. If 5 of 8 transmissions fail, the part sets an X-ready fault and turns off the FETs. The X-ready feature can't be masked by the MCU. The communications must be restored before the MCU can clear the fault and turn on the FETs. Cell voltages will vary with load. This affects the capacity as shown in this diagram, but also indicates the cell voltage will vary dynamically as the load changes. The inputs have a lighter filter than the power pins. As the cell voltages vary dynamically, the input voltages could be pulled below the power pin. VC5B is most likely in this diagram since it senses the same cell voltage as the power pin. VC5B has its power filter cap separated from the differential cap string to avoid being pushed below VC5X. The part cannot measure voltage below the power pin. With large voltage variations, current can be drawn from the input pin. The IC design comprehends this architecture. If this movement concerns the system designer, Schottky diodes can be added externally to carry the current. The basic measurement timing runs on a 250 millisecond scheduler timeline. Both the voltage measurement and Coulomb counter use the same timeline. The Coulomb counter integrates over the full 250 millisecond time, while the interval is cut into 50 millisecond segments for voltage measurement. Cells are measured sequentially starting at cell 1. Every 2 seconds, the temperature measurement is taken with time from the 5th cell. Each group of 5 cells has its own independent scheduler timeline, and they will drift with respect to each other. Cell balancing is accomplished by pulling the top and bottom sense pins for the cell together with an internal FET. The cell balance is controlled by the host. The device will duty cycle the balancing of the cell to provide measurement during the balance. Balancing is synchronized to the scheduler timeline of each group, and there will be a delay from the I2C command to the balancing action. Notice that rapid writes by the host to turn on and off balancing may not produce any balancing action. When cell balancing is operating, the scheduler timeline is split into 20 12.5 millisecond segments. Balancing is off for one segment to allow the input filter to settle. Measurement then begins in sequence for the 5 cells of the group. After cell measurement, balancing is turned on again. When it is time to measure temperature, that measurement is done following the cells. Since one 12.5 millisecond interval is allowed for settling, the input filter should not be made too large, or artifacts will be observed in the cell voltage. The bottom cell of each group is most likely to show any effect, since it is the first measured. Since the architecture requires the input filter resistors to be large for the BQ76930 and BQ76940, the capacitors are typically adjusted. The EVM uses a large filter, and voltage effects can be observed. For the BQ76930 and BQ76940, the internal balance current is limited by the large input resistors, and an external circuit is needed for moderate currents. When the VCN pins pull together for balancing, the cell voltage divides across the input filter resistors at the top and bottom of the cell. A small current flows through the resistors and IC. The voltage drop across the input filter resistor can turn on an external FET to draw current through a balance resistor for a higher current. Approximately half the cell voltage is available for the gate. Either N or P channel FETs can be used with these monitors, since resistors are used at both the top and bottom of each cell. The Zeners shown in the circuit do not conduct during balancing. During a short circuit or heavy load on the battery, the cell voltages may drop significantly while the IC input pins are held up by the filter caps. The large voltage across the input resistors may easily exceed the balance FET absolute maximum gate source voltage. The Zener and resistor limit the voltage for the FET and prevent excess current draw from the filter capacitors. This monitor family was designed for random cell connection, but it will have limits. Ground, or battery minus, is expected to be connected first. This is the reference for the IC. When a cell input is connected, the differential input capacitors divide the voltages to the inputs of the IC. This diagram shows connection of the power group second, where the current inrush will charge both the group power filter and cells. Notice that the voltages divide. The external cell balance circuit can have a significant influence on the pin voltages. In this example with p-channel balancing, cell 0 is routed to the battery separately from battery minus, and cell 4 is connected after battery minus. The inrush current will provide 16 volts across RN4, and the Zener will conduct. The cell balance FET will turn on. As the cell 4 balance FET turns on, it provides voltage to the RN3 resistor, which will turn on that balance FET. The effect continues down the input chain, turning on successive balance FETs. With VC0 open, this example of connecting cell 6 input second shows that a large peak voltage exceeding absolute maximum of the lower inputs can be applied to the device. By connecting VC0 to battery negative on the board, the large voltage spikes from the previous example are eliminated. When using N-channel FETs, the inrush current into the input filter resistor does not turn on the balance FET. The BQ76930 and BQ76940 connection diagrams show a required diode from the top group input to the power pin. The input capacitors are smaller than the power filter capacitor, and the input pin voltage will rise faster on a step than the power filter cap. When an upper cell of the BQ76930 or BQ76940 is connected, the difference in the voltage rise can easily cause a violation of the absolute maximum voltage of the input. The diodes shown in the datasheet are important to keep the voltage in limits, and their presence avoided a limiting specification from the top cell to power. A top cell input damaged from a circuit without the diode will typically report a lower voltage than applied. Random cell connection is listed as a feature of the device, but has no supporting specifications. While the part was designed to avoid sensitivities, it still has absolute maximum limits, and the components used can affect the device stress. In the example shown, cell 11 is connected, allowing the small C11 to take most of the voltage as the larger CF2 charges more slowly. The Zener diodes shown may provide benefit since the lower group cells have the lowest absolute maximum voltages of the inputs. Cell connection sequentially from bottom up provides the smallest voltage steps into the system. Connection of the group power from bottom up provides simultaneous power to the group and capacitive distribution across the inputs. Some users have noted shifts in the reported voltages of some cell groups where these groups are not able to meet the datasheet performance limits. These appear to be related to mechanical stress induced on the package during assembly from warpage or mounting stress. Reflow of the device has shown improvement. Avoiding warpage and distortion of the boards during assembly is recommended. The FET drivers are resistive drivers. The off resistance is shown in the datasheet. The charge driver has a high resistance to enable use of the load detection circuit. The on resistance of the drivers is not shown in the datasheet. A rise time is provided which can be used to calculate a value if desired. However, the nominal on resistance is 5K ohms. The FET outputs are designed to directly drive a moderately sized discharge FET on the low side and a charge FET through a simple circuit. The charge FET driver includes a circuit to detect when a load is present if desired. The charge output must be turned off for the mechanism to operate. The load is detected when the voltage on the PAC- pin pulls the charge pin above a threshold. Typically, with a load attached and the FETs off, PAC- will be pulled to PAC+. The circuit must limit current into the charge pin and prevent excessive gate voltage on the charge FET gate. Since the charge pin test current is high and the resulting voltage will exceed the gate source voltage limit of many external FETs, the cautious designer may want to add an external clamp zener at the charge pin. The speed and drive strength of the FET drivers is fixed by the internal resistance. With a single FET, an external resistor may be desired to slow gate switching speed. For faster switching or a multiple FET array, the discharge FET driver can be strengthened by adding an external driver. The charge FET switching speed depends heavily on the R2 gate source resistor. It can be adjusted with the trade-off of more quiescent current. A buffer for the charge FET will require a more complex circuit since the FET may float below ground, and a buffer will typically prevent operation of the load detect feature. The EVMs in many systems may have a flyback diode to clamp inductive transients on PAC-. These will short-circuit a reverse charger. In systems which require a reverse charger tolerance, the low side driver does allow this. In the reverse charger condition, after protection, the PAC- may be twice the battery voltage. The discharge FET voltage must be selected appropriately. The charge pin sense resistor must be sized to maintain current within acceptable limits. The BQ76940 family does have a gauge available, the BQ78350. This gauge is based on a proven microcontroller and operates with either the CRC or non-CRC version with 2.5 volt reg out. That is, the 00 and 01 suffix monitor devices. The gauge provides firmware-based protection limits and recovery using the monitor protections for faster response and secondary protections. The BQ78350 uses compensated end of discharge voltage CEDV gauging and has a SM bus interface. SM bus and many communication buses are low side referenced. When the BQ78350 communication is referenced to PAC-, significant leakage paths exist during fault in either charge or discharge conditions, which may also result in damage to the BMS unit. There are three basic solutions for the communications leakage. The first is isolation of the interface, typically electrically with an isolator device, which will require power. A second is breaking the communication during fault, which eliminates the leakage but does prevent communication. The battery is not able to report its fault condition, and the interface cannot assist in recovery. The third common solution is to use high side switching, either P-channel FETs, which have the control voltage in the range of the battery, or N-channel FETs, which require a voltage above the battery positive. The BQ76200 is a charge pump driver to allow high side switching. Thank you for your interest in the BQ76940 family devices. Remember that additional information is available on TI.com.